Hello, this is Peter. This is my submission for the extra credit assignment. And for this video, I'm just going to be going back and forth between the problem set and my solution for the problem set. I first labeled out what was given to me, which would be the forces F1 equals 70 newtons and F2 equals 40 newtons. I labeled out what to find, which would be F of R, the resultant force, the parallel of F1 onto AC, the parallel projection of F1 onto AC, and the perpendicular projection of F1 onto AC, and then theta, the angle between F1 and F2. I then laid out my plan, which would be I decided it would be easiest to first put each force into vector form, and that would make it really easy to find the resultant vector as we just add them together. To find the parallel component, we multiply the force that we have by the axis by the axis we want to project it on. That's the parallel component. We just take the dot product of those. And then to find the perpendicular component, we have this formula here where we have the magnitude of the force. We subtract it from the magnitude of the parallel component. And then to find the angle, we use the geometric dot product, which has the angle inside of it, and we solve that for theta. So just to follow through my calculations, I first put each force into vector form by I first have to find the unit vector. So for vector F2, we find the vector between AC, and we do that by subtracting the coordinates, or by taking the coordinates of C and subtracting the coordinates of A, and that will give us the vector. And this is what I'm doing right here, and we find that the vector will be negative 4i plus 6j plus k. And then to unitize it, we have to divide it by its magnitude. So to do that, we just square each component and then add it together and then take the square root. And that ends up being the square root of 53. Then we just multiply them together, and then we get this vector here, which is negative 21.98i plus 32.97j plus 5.49k. And we do the exact same thing for the AB vector in F1. We find that F1 equals 20i plus 60j minus 30k. And then all we have to do from here is, because they're already in vector form, we can just add them together, and we find that F of R equals negative 41.98i plus 92.97j minus 24.51k. Or we can write this as a magnitude, and we would do that by just squaring each component. Oops, sorry, it's much too thick. I'm sorry. There we go. We square each component, and we take the square root of that. So this is how we find the magnitude for any vector. This is how we did for here. Now, for the rest of the problem, to find the projection, we just take the dot product here, and me personally, I tend to leave the unit vector. I tend to always just pull out dividing by the magnitude, as I find it easier to calculate that way. That's what I've done right here. And we'll just take the dot product, and to do the dot product, we would, let me change the thickness again. We would multiply the I components by each other, the J components by each other, and the K components by each other, and then we add those all together. And by doing that, I found that the parallel component would be 56.32 newtons. To find the perpendicular projection, we subtract the magnitude which was given early in the problem, which is 70. We square that, and we subtract that from the square, or we subtract the square of the parallel component from the overall magnitude. And from that, we get that the magnitude is 41.56 newtons. For the angle, we have this geometric dot product. We know that the vector F1 dotted with the vector F2 is equal to their magnitudes multiplied together, and then the angle between them. And so we can write this out, and we can rearrange this for cosine theta, and then take the arc cosine, or the inverse cosine of that. And by doing that here, I'm just going through the dot product, and I'm just multiplying by the magnitudes which are given to us at the very beginning of the problem, which would be 40 and 70. And from doing that, we find that theta is 36.42 degrees. So for the second question, we are given this diagram, and we're asked to find the spring constant K given the mass of the box, which is 40 kilograms, and the unstrength length of the spring, which is 2 meters. In this problem, we start off by, drawing off the diagram and listing off our givens, our find, and our plan. And actually right here I've made a little typo. I've said 45 instead of 40, but in my calculations, as you'll see below, I actually do use 40, so we can just ignore that for now. That ends up not being an issue. So as we go through the problem, let me erase that. Excuse me. We first set up an FBD at point C, and we use our equations of equilibrium to we first find the angle between the x-axis and the force from the spring, which would be the tangent of 2 over 3, or which would be the inverse tangent of 2 over 3, which gives us an angle of 33.69 degrees. And then we find our f of x, and we just subtract the x component of this vector from the x component, or we subtract the x component of this vector from the x component of this vector, and we find that the vector FCD equals 1.177 times the f of s force. From there, we get our the next step, we get our f of y, and now that we have FCD in terms of f of s, we can just plug it in. We have one equation, one unknown. Here's the 40 instead of 45. And we find that the force from the spring is equal to 282.92 newtons. Then we find the separation of the spring from its stable equilibrium, which would be 2 meters, by subtracting that from the stretch length. And from that, we get 1.606 meters. Then we just use Hooke's law to know that the force is equal to the separation distance times, the strand, then we use Hooke's law to know that the force of a spring is equal to the spring constant times the length that it's stretched by. And we just do some simple rearranging, and we find that the spring constant is 176.21 newtons over meter. And we know that answer is probably right, because that is a pretty normal spring constant. Spring constants are generally, in the hundreds. I know for cars, I think they're about in the 10,000s. So this is a pretty average spring constant for this kind of setup. For the next problem, problem 3, we are first asked to find the tension in each cable if the flower pot weighed 20 kilograms, and then we're asked to find the maximum weight of the pot if each cable could only support 50 newtons. And for this problem, I found it easiest to first just go through each of the equations for equilibrium in each dimension, just to write out a system of equations, and then for each part we could solve each of them differently. We could put in our known variable and solve for them. So we first have to find the angle that each of these vectors TC and TD make with the y-axis, and they'll have the same angle as they both have the same distance from the y-axis, and they both have the same length of this component here. And we find that angle by just doing the inverse tangent. We find that angle as 26.57. Then we do the equation of equilibrium to find that TC actually equals TD. And then from there, we find the angle that TB makes with the z-axis, or from the y-axis but vertically. and that would equal 63.43, or the inverse tangent of 6 meters over 3 meters. And then doing some of the forces in the y dimension, we find that TB equals 4TD, or that TD equals 1/4 over TB. TB over 1/4. It's TB divided by 4. And this relation here is especially important for later in the question. And if we just sum all the forces in the z dimension, we find that it's only TB and W, and it's sine TB minus W. It's TB sine alpha minus W. And then from there, for the second part, we will plug in our known of W equals 20 kg times the gravity constant, which is 9.81 on Earth. We find that TB equals 219.37, and that TD equals 1/4 of that, which also equals TC, because TC equals TD from earlier on. We'll find that equal to 54.84 newtons. And then to find the max weight it could hold if each rope could only sustain 50 newtons, that's really easy because we already have a formula for the weight in terms of TB from doing all the equations of equilibrium. And for that, we just plug in 50 for TB here, and we find that W can equal a maximum of 44.72 newtons. They didn't ask to find the mass of this, but if we wanted to find the mass in this part 3, we just divide this by 9.81, and that'll give us a mass. So for the fourth question, we are asked to resolve this system into a single vector. And to do that, we first will add all the x components of the vectors. Then we'll add all the y components of the vectors, and now will give us the x component of the resultant vector and the y component of the resultant vector. And then to find out where it acts upon, we will do the moment about A, and the moment about A will equal the resultant moment from this vector, and that we can solve for D that way, which is what we have here. To solve the third question, we will first, list our givens, which is that this force here is equal to 450 newtons, the force at B is equal to 300 newtons, and the force at C, I'm not actually sure if that's C, but just the point all the way over here is equal to 700 newtons, and then there's a moment acting at this point that is equal to 1,500 newton meters. So to find f of r, we will first sum all the x forces, which would just be, this times the sine times the cosine 60, this times the sine of 30, and we find that that equals 125 newtons. Let's write that down here. Then we sum all the y components of each vector, and we see that equals to negative 1296 newtons. And this is also negative. And then we could find the magnitude, or we could just leave this in vector form as negative 125i minus 1296j newtons. And I personally find it much easier to leave it in that form. And then to find the distance of it, we will first have to assume where the f of r acts. I just assume it acts at some point in the middle because there's no real space on the... Wouldn't make sense for it to act here just given the diagram to the left of A, just given the diagram. I think it'll act somewhere in the middle. And to do that, we just set the f of r y times d. Everything is with the y components, as there's no dy here, because just everything acts in the same plane. They all act in the same y values, so there's no dy. So we use the y component times the x component, or times the x distance from point A, and by going through this, we find that d equals 7.36 meters. Now, for the next question, we are given this body, we're given the distributed loading, and we're given this weird little bent elbow shape, and we're asked to find the reactions at roller A and pin B. Now, the fact that it's a roller and a pin is very specific. A roller only has one reactant force, and that is perpendicular to the ground, because the force reactions are created by restrictions of movement, and a roller is free to move. Let's say this roller here is free to move. There's nothing stopping it from moving this way, rolling this way, or rolling that way, but the normal force of the ground prevents it from moving down, so the reactive force is pointing up, like that. A pin can let you rotate so there's no reactive moment, but you can't move in either direction, so there's a reaction here and a reaction here. And then there's a Y reaction and an X reaction. And from there, we first will resolve. Well, we're given that the distributed loading is 3,000 newtons over meters, sorry, and that this length is equal to 3 meters. And we first resolve the distributed loading into one force, which would be just, since it's a rectangle, it's a simple shape, we can just multiply the distributed loading by the meters. We find that to be 12 kilonewtons. And the centroid, we don't even need to calculate. We know will be in the middle of this rectangle, which is 4 meters long, and so that would just be 2 meters. Now, we find the moment at B, and since there's no dx or dy for b of y or b of x, those cancel out, and that gives us a way to find A. And to find A, or just to find this moment, to resolve this, we have 12 newtons acting at a distance of 2 meters, and then we have the x component of this force here, which would be A cosine 60 times the y distance from this, which would be 3 sine 30, and then the y component times the total dx, which would be 4 meters, plus this distance here, which would be cosine 30 times 3 meters. And from that, we find that the reaction at A is equal to 3.714 kilonewtons. And then from there, we just do some equations of equilibrium. And we find that B of y equals 8.78 kilonewtons and B of x equals 1.86 kilonewtons. For the next question, we are asked to find the reactions at fixed support A. Now, as I mentioned, reactions are created by restriction in movement. Because this is a fixed support, that means it can't move in any way, so it will have 6 reactions. List off what we're finding, and then lay out our plan. For this one, the plan is really simple. We are just doing the equations of equilibrium. There's not much more to it. So we are given that we have a force in the x dimension that is 400 newtons, so negative 400 I. We have F2 is positive 500 J, where the F3 is negative 600 K. And we first just do our equations of equilibrium, and we find that A of x is equal to 400, A of y is equal to negative 500, and A of z is equal to 600. Now, to find the moment, we will multiply, so the moment about x, for example, we will multiply each of these forces by their distance from the axis. And if, for example, like this 400 newton force here, the reason that doesn't create a moment is that it's parallel to the axis. There's no way to do the right-hand rule to have this give a clockwise or counterclockwise force in the x dimension. So by doing that and doing the right-hand rule, we find that the reaction of MAX is equal to 1,025 newton meters, then M of y is equal to 750 newton meters. When we do M of z, there ends up not being a reaction because this force here acts on the z-axis, so there's no distance from the z-axis, so it's just 0. And this force here is parallel to the z-axis, so it can't, we can't have that be a moment. And then this 500, this y equals 500, the only distance we're given of is in terms of y, and to find the moment, you have to multiply it. You have to multiply the arm. You have to multiply the force by an arm that's not in the same dimension as it. So we can't multiply this 500j vector by one r, because that would just wouldn't work. So we find this out. We end up with these answers, and then we move on to the next problem. For the next problem, we're asked to find A, B, A, I, E, D, and E, F. And for this, I found it best to do method of sections. We're given all these applied forces and the distances. We will first do global equilibrium to find the support reactions. And we first do f of x to find that E of x equals 3.5 kip. We'll do the moment about E, and we find that A of y equals 1.5 kip. And then we do f of y, and we see that E of y equals 4.5 kilo and kip. And kip is 1,000 pounds. It's a very odd naming convention. Now, to find each part, we will do the method of sections where we make cuts through the sections that we want to find the internal forces. So we first make our cut 1, and we draw an FBD for it, and we simply just solve that. We solve the equations of equilibrium for it, and we find that AI equals 4.05 kip. Oh, and something I forgot to mention, we're supposed to find if our tension or compression. And when we're doing truss analysis, essentially we first assume everything is in tension, and that means that it's pulling away from the force from the point that we're analyzing. So a positive value means that it's in tension, and a negative value means that it's in compression. So we find that A of I ends up being negative, so it's actually going in, and that would be 4.04 kip in compression. And then AB is 3.75 kip in tension, because it pulls out, it stays positive. Oh, and we have to first find this angle theta here, and we just do that by doing the arctan, or the tan inverse tangent of 4/10. Here, it's the same solution. We first find the angle alpha by doing the arctan of 4/10, which is 21.8 degrees. Then we do the sum of the forces in the y dimension, the sum of the y direction. Then we find that E of F equals 12.1 kip in compression. Then we do the sum of the forces in the x dimension. We find that ED equals 7.73 kip in tension. Now, for the next question, we are given this. We are given an active force of 4 kilonewtons here, 8 kilonewtons here. We're given the distances. We're asked to find AF, BF, and BC. And once again, it's a truss analysis. We first start off by doing global equilibrium to find the support reactions. There is a pin here, a roller here. So there is one support reaction in the y direction here. At point A, there's a y and an x reaction. And by doing the global equilibrium, we find that AX equals negative 12 kilonewtons. B of y equals 21.33 kilonewtons. And F of y, or A of y, equals negative 21.33 kilonewtons. From there, we go within the method of sections, where once again we will cut everything we want to find, and when we're doing the method of sections, you don't want to cut more than 3 sections, because each cut you make is another unknown, and we only have 3 equations to analyze at any point. So if we make more than 3 cuts, then we have more. We will have, let's say we cut 4 beams. We'll have 4 unknowns and 3 equations, and that's just not possible to solve. So if we limit ourselves to 3 cuts, we'll have 3 unknowns and 3 equations, and we can solve anything like that. So we make our cut. We cut everything we want to find. We end up with a diagram like this. We first find the theta, which would be, we first find the angle theta, which would be the inverse tangent of 2 over 1.5. And that's 53.13 degrees. We do the sum of the forces in the x direction, and that would be, we find that BFF equals 20 kilonewtons in compression. We find that M of B, which would cancel out our 2 unknowns here, and just get, it would actually cancel out quite a bit. It cancels out BF, BC, BY, or B, and then we have just A of X and A of Y, or we already know A of X and A of Y, and now let's just find A of F, when the A of F is equal to 21.3 kilonewtons in tension. Then we just do the sum of the forces in the Y dimension, the Y direction, and we find that BC, the internal force BC, is equal to 5.33 kilonewtons in compression. Now for the next question, we are given a frame. And frames are a little tricky. So to solve this question, you first want to draw it as a whole, and I actually find it easier if we split it we try to split into two or more members. So for this one, we'll split it into member AC, so just this part, and member BC, which is this part. And we're looking for the reactions at A, B, and C. And we first want to resolve this loading into one force, and now to do that, we first need to find the length of this segment here, AC. And to do that, we know the height, we know the angle that it's at, and we know the total height of it. We can just use the right triangle to find that the total length is 2.309 meters. And then we can resolve this whole thing into a single force, which would be 461.8 newtons. From there, we we analyze just point AC. So we just look at this half, and we'll do our equations of equilibrium. And what we're doing is we're setting up a system of equations for C of Y, because that is like the common denominator between section BC and section AC. And we do our moment about A, and we know that the moment from a distributed loading is just equal to the force from the distributed loading times its centroid. So we don't need to worry about the distance from A because it's acts at A. We don't need to worry about the X or Y component, because we are finding the distance is already in terms of this angle, already in terms of like the sine angle 60. So that puts us in a fortunate situation. And we just go through the whole moment about A, and we find the equation that C of Y, or that we find that negative 2 C of X plus 1.155 C of Y equals negative 533.1. Analyzing BC and taking the moment about B, we find that negative 2 C of Y plus 2 C of X equals 1,600. And that gives us two equations. We have two unknowns, and we just simplify from there. We just solve from there. So we plug in, we add these together to cancel out C of X, because we have a negative 2 C of X, and we have a positive plus 2 C of X. We just add those together, and we find that C of Y times negative 3.155 equals 1066.4. Then we can solve that. We can just divide that by 3.155, and we find that C of Y is equal to negative 338 newtons. C of X, we know, is, we have these equations here. We see that C of X is equal to 462 newtons, and the total reaction, I didn't write it down here, but you would just find it by doing C of Y squared plus C of X squared, and taking the square root. It's just the same thing as always. And we find C to be 572 newtons. Now we go down. We do the now we can just do now that we have C, and we have things in terms of C from earlier. We just plug C back into these equations of equilibrium for AC and BC. We find that B of Y equals negative 338 newtons, B of X equals 338 newtons, and then we find that this equals 470. We find that the total is equal to 478 newtons. For F of Y, we find that segment AC, sorry, we find that f of y, we can find the sum of the forces in the y direction gives us a of y equals 569 newtons, and a of x equals 62.1 newtons, and we find the total A is equal to 572 newtons. Now, for the sliding block problem, frames and friction, we are given the mass of each block, which would be 5 kilograms. We're given the angles here, and we're given the coefficient of static friction, the static coefficient of friction. And for this problem, I found it easier if we first analyze C, A, and B to get the frictions, just to get things in terms of P, the force that we're the thing that we're finding, and in terms of the normal force, or in terms of the frictional force. And we're asked to find the largest P that we can have without there being any moment, or without there being any movement, sorry. And we first, we have our givens, MB equals MA equals 5 kg, and the constant of friction equals 0.5. We first analyze A, and we just do the equation of equilibrium. And what we do is we do the equations of equilibrium, and then we just put things in terms of P. We find that FAC equals 1.732P, and FBC equals 2P. And since this is static, we act like this force here is like tension, where it pushes out on each side equally. And then from analyzing 2, we find that, we have our force, we have our friction acting against the motion. This thing is pushing in this direction, so the friction acts against that and pushes back. Now, the normal force, it can be anywhere anywhere between this region. I just draw it at the middle for simplicity's sake. We can't analyze any tipping here because we're not given the total length of each block. So, we go through our FBDs here. We set up our equations of equilibrium, and we solve these, and we find that F of A, the friction at A equals 1.5 P, and the normal force at A equals the weight of the block plus 0.8660 P. And we know that the weight is just gravity times 5. For 3, it's the same thing, but I personally found it easier if we tilt the axis to match the box, as we're solving for FB. We're solving for NB and FB, and we're gonna need to divide those angles, those cosines and sines anyways. It's easier to just get that out of the way and just put them at an angle. Put the things coming in at angles. And by just going through our equations of equilibrium, we find that F of B equals 1.732P minus W over 2. The sine 30 equals 1/2. And NB equals P plus W cosine 30 equals 0. Or, that's just the equation of equilibrium. Now, we have to do both. We have to do two things. We have to first check if it will slip at A first, and we have to also check if it will slip at B first. And we find each of those, and we compare which one has the lower P, and then we'll take the one with the lower P, as that is, the largest P without any motion. Because if we go with the larger one, by the time block B is already moving, by the time block B will be moving, block A is already moving. And when we assume that it's slipping, we know that the friction is equal to the coefficient of the friction constant times the normal force. And we just we substitute in US equal F of A equals US and A into the system of equations earlier, and we get these system of equations. We just solve that, and we find that P equals 23 newtons. We do the same thing here. F of B equals 0.5 times the normal force at B, and we find that P equals 37.2 newtons. The P at A is less than, so we know that P equals 23 newtons and that A will slip first, or A will fail first. So for the chapter 7 question, we are given this configuration here. We have this rope acting here, which will give us a tension force here, a tension force here. We have a moment acting all the way at the end, and we're giving all these distances. So to analyze this, and we're asked to find the internal forces at point C, which is right here. To analyze this, we first draw a diagram. A will have two reactions because it's a pin. There's just one reaction from B because there's just pulling in one direction. And to find this, we first will do global equilibrium. We first do the moment about A. We know that this force acts in the x direction, so we'll be using the dy. So it doesn't really matter where we could put this force. You could put this force right here and ignore B of y and just call this the tension force. It doesn't really matter. It gives us the same answer. And to find the dy, we're given the length to the center of this circle and the radius of the circle. So we just add those up, and we'll find that the total distance is 2.5 feet. And then we have the M of A will just be the tension force in the x direction times 2.5 minus this clockwise moment here, and then, minus the tension force pulling down all the way at the end times the distance from A, which would be 12 feet. And we find that B of x equals 280 pounds. Then we just go through the standard summing all the forces in the x and y. We find that A of x equals 280 pounds. We find that A of y equals 50 pounds. Then to find the moment at C, we will cut everything off on the left side to find the internal forces. And by cutting, we know that since it's on the left side here, since we're looking at some cut here, that this is a positive shear points down, and that a positive moment will point here, and that the internal normal will always point outwards from the cut. And here we just do some standard equations of equilibrium. We find that from f of y, or the sum of the forces in f of y, we find that V equals 50 pounds. We find that from the f of x, we find that the normal force is equal to negative 280 pounds. And by doing a moment at C, we find that the moment of the internal moment is equal to 150 pounds times feet. For the next problem, we're asked to find the shear and bending moment diagrams for this beam. And to do this, we'll divide this into the 4 sections where each new force gets added, as shown here. But first, we will do our global equilibrium to find the support reactions. And before we do that, we have to first resolve this into one force. And I've actually skipped that step here because it's pretty trivial. You just multiply 10K by 2, and you get 20K newtons. So doing global equilibrium, we do the moment about A, and we find that B of y equals 25 kilonewtons. We do the sum of the forces in the y direction. We find that A of y equals 10 kilonewtons. And doing the sum of the forces in the x direction, there is only A of x, so A of x equals 0. So now we split into sections. And what we'll do is we'll do this section and we'll cut off right before we encounter a new force or a new moment or something like that. And let's say if we say we have a new moment being added, that will be represented by a sudden jump in our graph, and then it'll go back down. And an important thing to remember when making the graphs is that the shear is the rate of change of the shear force is the rate of change of the moment, and the distributed loading is the rate of change of the shear. Just some things to remember making your graphs. So splitting into sections, we do 0 to 2. We find there's not much going on. We find v equals 10k, m equals 20k. Doing x from 0 to 3, we get this new 15k force, and now this is farther away. The point that we're analyzing with the shear and the moment gets moved further away. We find that v equals -5 and m equals 15. Doing up to 4k, we get this new moment added. Oh, excuse me. We get this new moment added, and that that jumps up our moment by a lot. And our v is still the same because no new forces have been added, but our moment increases by about 15k. So when we get to greater than 10k, we don't actually have to analyze this, because what we know is that at the end, this will have a magnitude. If we were to analyze the shear at just this point, we know it would be going down. We know it would be opposite this. It would be a 25k at each side. The total magnitude is the same as the support reaction. If we're just at a support, it's the same as the support reaction, the shear. So we know it has to equal -25k, and we know that the shear is its rate of change, so we can just represent that on our graph. So here we have our 10k from 0 to 2, our -5 from 0 to 4, and then from 4 to 6, we linearly decrease down to -25 because the rate of change is -10x, right? We know it has to go down. So for the moment, since the shear is the rate of change, we know at 2 it equals, we know at, did I forget to draw on 1? Let me double check this. Excuse me. Okay, no, we don't need to draw on 1. So we know at 2, it goes from 0 to 2, it goes from 0 to 20, and then it's all linear. These are all linearly changing because the shear is constant. These are all linear change. When we get to 3, we see that sudden jump from 15 to 35, but as we get down to 4, it linearly decreases down to the value that we calculated. Now, when we're here, we see that now dv is linearly changing, so that means the derivative of this is decreasing. But it's already negative, so it's increasing negatively, which means this is a concave down graph. It's decreasing negatively as we go. A concave up graph would be if the loading, for example, is positive, maybe the moment would be like this, but that's just not the case in this scenario. And something to mention for these moment diagrams is that the moment must always start and end at 0 if there is no moment happening at the supports, right? Our supports here have no moment on either side, so we can't actually see a non-zero moment on either side. So for the next question, we are asked to find the y centroid measured from the top. This is pretty straightforward. We do the table method. We have our sections listed here. We break down this composite body into like the simplest shapes as we can, which in this case would be 2 rectangles and a circle. We find the area for each shape. We sum it all together. We find the y tilde for each shape. We don't have to sum it together because that's not useful for us. But then we multiply each area by its y tilde, and we sum that together. And then we can plug it into this formula here. When finding the y tilde, you generally find the center of the shape. These are all pretty simple shapes. So the center of a circle is just in the center. The center of the rectangle is just in the center. But when we're down here, let's say, we have our y tilde at 50 millimeters inside the circle, but we also have to add this entire distance. It wouldn't just be 50 millimeters, but it would be 50 plus 150 plus 15. That would also go for the rectangle here. It wouldn't just be 75, it would be 75 plus 15, which is represented here and here. And then we calculate this all, we put it into our handy little formula, and we find that y tilde equals 154 millimeters. In this problem, we're asked to find the moment of inertia with respect to the y-axis and the moment of inertia with respect to the x-axis, given the two functions y squared equals 2x and y equals x. And also given the fact that their bounds are from 0 to 2 in both dimensions. This is also a pretty straightforward problem. We are plugging in this formula, we just change it around. We're just plugging in this formula, we change it around for which one we're doing, so I of y would equal x squared dA. And the most important part of this problem is to set our dAs right. So when we're doing the first one, we need our dA in terms of y because we have the y squared component here. And to do that, we have our dy, it would just be like this, right? Where just our dy is just straight up from the x-axis. But our dx is a bit more complicated because we want this x area inside of here. So that would end up being x minus 2x, right? Or in this case, we're doing y minus y over, right? It's x2 minus x1, where we have this is our x2 function and this is our x1. But we have to solve these for x. This is already solved for x because they're linearly. But for this one, to get it in terms of x, we just need to divide both sides by 2. And we find that right here. And then from here on to simple integration, we just integrate it from the bounds of y. So this is a simple power rule. Oh, and you have to multiply this by y squared. This is a step I skipped. I already did it in here. Just instantly plugged it in. This is a pretty simple power rule. Just remember to bring down that 5 so you get y to the 5th over 10 instead of y to the 5th over 5. And you get 0.8 meters to the 4th. Same thing for the I of y in our moment of inertia with respect to the y-axis. Our dx would be this area, but our dy would be y minus y. Sorry, I'm so sorry. Y2 minus y1, right? Because we have this upper function minus this lower function, and we solve those both for y. So we take for this top one, we have to take the square root on both sides, and we get this formula. We multiply this through by x. So this is this is 3 over x. This would be 3 over 2x. I'm sorry, and that's because we multiply this by 2. This is to the 1/2. You can write square root x as x to the 1/2, and we calculate this through. We just integrate this again. This is a pretty simple power rule. Just make sure to flip the exponent as we bring it down. As we take x and we divide. We have like x to 3 over 2. And we divide it basically by 2 over 3. It's not the same numbers, but it's the same idea. Dividing by 3 over 2 is the same thing as multiplying by 3/2. And for this one, we find that the moment of inertia is 0.571 meters cubed. So for this last question, what we're doing is we're finding y bar, ix, and kx. Y bar and kx are pretty straightforward. Kx is just plugging in this formula, and kx is the gyration. And the y bar is pretty simple. We're just taking the area of each shape and we're adding that together. And we're finding the y tilde of each shape. We're multiplying it by the area of that. And then we sum the area times the y tilde. Divide that by the sum of the areas to find the y bar. Same thing, just the same thing we did before. We find that y bar equals 0.54 meters. And moving on, we need to find I with respect to x. So how we do that is we use the parallel axis theorem. So what we do is for each section, we find its ix and that is done with the formula of Ix, the Ix with respect to the centroid plus its distance from the distance between their centroids in the y dimension. So that's why we need to find y bar earlier, is that this problem will not be doable without it. So, but for that section, for each shape, we find its I of y, we add that times its area times the distance from the centroid. The centroid for this shape is about here. It's actually a little bit above here. It's about 0.5, so it's about here. So it'll be this distance. That's how we approach these problems. And for this one, I use the table. That's what I recommend you do. It's a much longer. You can integrate it. It's a pretty simple integral, but you can just plug in the formula. For the I of x, it's just 1 over 12, the base times the height cubed, and then plus a dy squared. And you just follow that through for each shape. And you just do that for this one. You do it for the middle part, and then you do it for the top part. And then you just sum it all together. And we found that the total moment of inertia with respect to the x-axis is 0.165 meters to the power of 4. Now for the k of x, you just plug in k of x equals ix over a, and that's all there is to it. And you just find that's how you just find. You just plug and chug, and that we find is 0.643 meters. So that is my solution. Yeah, thank you.